So now we know about symmetric key encryption, asymmetric or public key encryption, and hybrid systems that use both. Now let's talk about digital signatures. A digital signature. What are they and what are they used for? They are, the name as it implies, it's an electronic signature. Just like the signature that you sign something on with a pen, it's just that this is in the electronic form. What does it really do for people? Well, number one, the sender authentication, which means someone can say that this actually came from you. It can also verify the message integrity to make sure that that message that was sent from you was not altered while it was going through the internet to the intended receiver. It's similar to a notarized document, and in a lot of states, it is legally binding. First question you have to ask yourself if you're going to digitally sign something is, should the message really be digitally signed? How important is it to know that the message came from Julie, a trusted source? How important would it be to know that the message hasn't been changed? In this example, the original said to sell your stock. So what are the steps involved? Well, the first step in a digital signature is to establish message integrity. This is normally accomplished through the message digest, also called a one-way hash function. The one-way hash function generates a message of authentication. Basically, it codes or hashes a value for the message. What is a hash value, you're going to ask? And that is a numeric or alphanumeric representation of the original message, similar to the sum of several numbers. You've already learned about MD5 hashes. This is the same, except it's being done to a message instead of a file. An example, just as 8 plus 4 plus 10 equals 22, a hash value for a message can be represented by a single string of characters. Buy lots of stock could equal the number that's represented here. It's an algorithm that looks at all the text inside the message, assigns it a numerical value, and then represents it as a hash or a numerical value. So why do we do this? Well, a digital signature is very much like a fingerprint. It's unchanging. The same message will always produce the same hash. It is unique. In theory, different messages never produce the same hash, or another word for that is a collision. So that every message, if the message was very much like a human fingerprint, the hash for that sentence would be the same every time you hash it. It would never change, unless you changed a portion of it. Let's say at the end, instead of a period, we put a comma. Then the hash for that message would be different, because the message itself is different because of the comma. Now we'll get back to what we learned so far. For the second step of a digital signature involves the public key encryption. The hash value is encrypted with the secret key of the sender. The receiver must have the public key of the sender to decrypt the hash value. Let me repeat that again. The hash value is encrypted with the secret key of the sender. So the recipient must have the sender's public key if they are to decrypt the hash value. So really what that means, if the receiver can decrypt a hash value with the alleged sender's public key, then the message is authentic. And we know it has to be authentic because we've already learned that only the public key of the sender can decrypt the sender's private key that encrypted the hash value. So now we know the sender is authentic, and we have a hash value that's authentic. And now we generate a hash value for the message itself and compare it to the original. If those two hash values are the same, then the message has not been changed from the time it was created, signed, or sent. The message integrity is now verified completely. The sender identity and the message content can be trusted by the recipient. So a quick overview. We create the message. We generate a hash value for the message. We use the sender's private or secret key to encrypt the hash value. We then send the message. So the message is received. We decrypt the hash value for the sender's public key. Next, we generate the hash value and compare to the original value. Is it the same? If it is, the sender authenticated and the integrity of the contents of the message have been authenticated. Thusly, the contents can be trusted that it came from that sender. Sounds like it's a foolproof method. Are there any potential problems? Well, authentication. Message recipients assume the sender's private key is secure. What happens if it's not? There was a word macro called Coalinga virus that checks to see if there was a copy of PGP installed on a machine. If the program was there, it looked for the user's private key ring, and it silently uploaded it to an FTP site on the internet, thusly making the person's private key now public. That is one of the failures of the two-key system. Another area is authentication. The message recipients always assume the sender's private key is secure. And they also assume that the secret key has not been shared. The secret key is a passphrase protected, and the passphrase has not been shared or easily guessed. Another potential problem with digital signatures can be the message integrity. If you cannot trust the messenger, you cannot trust the message. There's more to worry about than the integrity of the message. How about the integrity of the sender? So the encryption weakness. How does that affect you when it comes to doing forensics? Number one, if you have a suspect and you try to establish a link between the file contents and them. Plain text and deleted files may hold the key to the encryption weakness, the private passphrase or private key. People write down passwords all the time because they can't remember them or they're too long to remember. So look around. They may be written down someplace. Some people have even gone to court, such as Woodland, California, where the judge ordered the suspect to produce the passphrase for the encryption. It was not a violation of his Fourth and Fifth Amendment rights because they could not tell the jury where they got the passphrase. All they could say is, the encrypted file contained the following. Viruses. Viruses sometimes can be on a machine, find those passphrases, record keystroke loggers, record them on the system, and they're there for you to find also. Come back to key logging, like I said a few minutes ago. Then you have encryption weaknesses that can be exploited by programs such as Access Data in Provo, Utah, or Elcomsoft. Well, that's it for this lecture on double key encryption and digital signatures. You've learned a lot and you've absorbed a lot in the last slides. The important part is this is a very important and upcoming field in forensics. Today we have ransomware out there and it's being thrown around in groves all over the internet. People are making hundreds of millions of dollars doing ransomware where they break into a system, hacking in, and then using encryption to encrypt all the files in the system and then holding the person who owns the data hostage for bitcoins. With your knowledge now of slack space, erase space, and as well as the basics of encryption, you might be able to find decryption keys in the slack space or unerased space. I've had many cases where that was the case, that the bad guy had to encrypt the files and then he deleted what at least he thought he deleted, the encryption program that encrypted all the files on a system. Once we found that program, we were able to reverse engineer the program, figure out how the encryption worked, and then develop our own keys to decrypt all the files. You'll also learn in later lectures sources that you can go to for both programs that can help you in decryption, as well as sources that can help you figure out decryption. But that's for another class and another lecture.